Welcome, everyone. My name's Matthew Scott. I'm president of the Carnegie Institution for Science. Very happy you braved the hot, humid weather to come out tonight. Now that we have proper HVAC in this auditorium, it's less of a sacrifice than it used to be, so we're happy about that. I'm excited to introduce my friend Kwabena tonight. He's someone I've admired for many years, a really original thinker, wonderful person, so it's thrilling to have him here. Let me tell you a little bit about his interests and work. In March 2016, artificial intelligence enthusiasts cheered when AlphaGo, a supercomputer created by a little company called Google, won 4 of 5 games of Go against a world champion human Go player. Depending on how you look at that, you're either sad or happy or something else. Go is one of the most complex games, even more complex than chess. And for many, this supercomputer victory represented an artificial intelligence milestone. Lost in the small print was the fact that AlphaGo the computer needed approximately 1 million watts of power to perform its task, while its human opponent used only 20. All right! Okay, so that was good from a certain standpoint, right? Building computers that use energy as efficiently as the human brain is a goal of our guest tonight. Dr. Kwabena Boahen is a pioneer in the new field of neuromorphic engineering. He and his colleagues at Stanford University have developed a neuromorphic system called NeuroGrid that simulates the brain's cerebral cortex, one of our favorite parts of the brain. Consisting of 1 million electronic, quote, neurons, unquote, connected by billions of synapses, NeuroGrid processes the same amount of information as a comparable supercomputer, but consumes 100,000 times less energy. Dr. Boahen and his colleagues are now working with other Stanford scientists to develop prosthetic limbs controlled by NeuroGrid-like chips. In addition, they are working on a silicon retina to help the blind and a self-organizing chip that simulates the brain's development. As a developmental biologist, I'm particularly interested in that last one. Dr. Boahen is professor of bioengineering and electrical engineering at Stanford, where he also directs the Brains in Silicon lab. A native of Ghana, he moved to the US to earn his BS and MS degrees in electrical engineering from Johns Hopkins University. He later received his PhD from Caltech, where his advisor was Carver Mead, who is generally considered the father of neuromorphic engineering. From 1997 to 2005, he was a bioengineering faculty member at the University of Pennsylvania, where he was Skierkenich Term Junior Chair. Dr. Boahen has published more than 80 articles, including a cover story in the May 2005 issue of Scientific American. His TED Talk, which is called A Computer That Works Like the Brain, has been viewed by 500,000 people, each of them consuming about 20 watts. In 2010, he made Esquire magazine's list of geniuses who give us hope, which is especially a nice thing, I think, for such a wonderful person. He's received several prominent awards, among them the Career Award from the National Science Foundation, the Director's Pioneer Award, and the Director's Transformative Research Award, both from the National Institute of Health, and the Young Investigator Award from the Office of Naval Research, in addition to a Packard Foundation Fellowship in Science and Engineering. He's a fellow of the Institute of Electrical and Electronics Engineers and of the American Institute for Medical and Biological Engineering. Please join me in welcoming Kwabena Boahen.
Thank you so much, Matt. I'm really pleased to be here, given that I get to see Matt. I haven't seen him about 2 years. He's been on this job for like 3 years. And, I'm out of shape. I don't bike as hard as I used to when I used to bike with him. So we need Matt to come out more often to California. Are we good with the pictures? Okay. So We'll dive right in. I always like to start by introducing the people who do the work. I've had the privilege of working with some really smart people, both at Penn and at Stanford. And so, yeah, it's been really wonderful. And this is how you're going to really hear about the work that they did in this talk. And so Matt mentioned this in his introduction. The earliest, I did my thesis, my PhD thesis at Caltech on developing the what's called a silicon retina. Basically, what you see here is the layout of a silicon chip. And silicon is really wonderful in that it can sense light directly. So you just expose part of the chip to light. And, this whole dimension here will be a few microns, so it's really much smaller. And we are actually, unlike a regular camera, we're emulating all the processing that goes on in the retina, which is 3 layers of cells deep, before then it's transmitted down the optic nerve. Okay, so it's already extracted features and so forth. And what you see here in this movie here are 4 different colors, red, green, yellow, and blue, for representing the activity of 4 different types of features that we are extracting right there in the chip and sending out as spikes on the optic nerve. And so this is Kareem Zaghou, who developed this silicon retina here for his PhD thesis. And this is a reconstruction. We didn't have that many pixels back in early 2000s when we did this work, but we actually are really duplicating the kind of processing that the retina does in this camera, using very little power. And, we also have modeled the cochlea, which is we have the outer ear, the middle ear, and the inner ear. So this little coil-like thing is a fluid-filled chamber that basically is able to detect frequencies by basically, it's set up such that different frequencies will cause the biggest vibration or amplitude of vibration in the fluid and also in a membrane that divides the fluid at different positions in the cochlea. And this is how you're able to tell the pitch of the sound or the frequency and so forth. And it's actually a mechanical device, and we were able to simulate that. So the noise you just heard was the sound, we call it the egg drop sound. And this is the response of the chip that you see here. These are activity of different kinds of, this would be, a snake-like, structure with different segments, and the going from the base and the apex as the thing dropped, and it was going lower in frequency. You're seeing the activity happen at different positions because it corresponds to that, and this is time. And so we've also worked on, actually, as Matt mentioned, we also moved on to the cortex, so all the sensory information that's pre-processed and encoded by the sensory organs then ends up in the cortex, and the cortex is a multi-layered structure. These are individual cells in the different colors, and this whole height here is about 2 or 3 millimeters, and it's about the size of a large pizza that's sort of crinkled up inside your head. And that's basically where people believe all our cognitive ability arises from. And we worked on taking that, so this is sort of depicting this columnar structure here. And this is neurogrid, which allows us to model these kinds of structures very efficiently. And here's basically a little animation here showing you the various layers of these cells. The little white activity you're seeing here is the spikes of individual cells. We've set up an experiment where we can cue. This is sort of supposed to be the working memory, and it remembers some input that was delivered to it, and that causes it to pay attention to one position rather than the other, and hence you get a stronger response at that position than the other. And I'm just walking you through these to give you an idea that we basically have been able to basically model perception, cognition, and also action, actually motor behavior with these silicon chips. And so here in this paper here, we were able to control a robot arm, like you see here, with neurogrid. And this control corresponds to basically trying to activate the 3 motors in such a way that you apply the right force, you move the end effector in the right direction, and basically you have to basically do some computation based on the current joint angles and the force itself and get the torques. And those were actually done by the neuromorphic chip in this case. And so here's I think the movie will start. Here's a movie here where you see my graduate student, Samir Menon here, basically interacting with the chip. It's showing you some of our hardware devices. And this is, the robot is basically trying to reach this green ball, which Samir is moving around. And the CAD model of the robot is rendered based on the current joint angles. And that information is sent to NeuroGrid. You're seeing the activity of 5 populations of neurons correspond to these 5 pools here in NeuroGrid, as well as their spike in activity. And it's basically able to track the ball really well, showing that it's actually doing the right transformation from joints of angles to force, applying the right torques. And here, Samir has just demonstrated that it's safe to bump into this robot because it's basically trying to apply a force. It's not trying to go to a particular position really hard. And it will just comply based on the force it's trying to apply. If you push back, it will comply. And so that's designed to work nicely around people. And so where are we going with this kind of technology, right? Okay, it's not only in California, huh? But anyway, so these cars drive themselves, not completely, but they're getting there. And, that's basically giving computers perception, right? Trying to emulate the perceptual capabilities of humans have. And that's where we're going with this technology. What else could we do? This is the goal. Well, Champion is now a computer, which, as Matt mentioned, and really the most interesting thing about this is, people thought that it was going to take another 10 years before computers will be able to master Go. The reason why they thought that is that Go is just exponentially much more. So many moves, so many possibilities. If you just brute force try to search for the best move, you'll be here till the end of the universe. It's like that complicated. And so the way that humans play this and are good at this is that they use intuition, right? They don't actually brute force search everything. They concentrate on some part of the board. They have the intuition that this is where you should look, and maybe this kind of move, and this area is the important part of the game right now. And for Google to be successful at doing this, they actually used a network, or they programmed the computer to do what the brain does. They program a network of neurons. These are sort of mathematically abstracted neurons. And they show them tons and tons of Go games. And they were able to capture that intuition in a neural network. And that's why they were able to do this. Basically, the brute force approach wouldn't work. And so it happened much faster than we thought it would. Okay, and so that's really interesting. So now we're given on computers intuition, and we also, anybody have a kitchen like this? Okay, would you like one? So it would be wonderful. You just say, hey, what do you want for dinner? And you tell it, and it would cook, your fresh made meal, and the robot arms and the Tyson jumping. You can't do this right now, but we're getting there where we are actually also starting to get these sort of motor skills, trained networks, neural networks to control robots and so forth. So that's all progressing at pace, but it's sort of like a big mismatch between the way the brain works, and trying to force computers to work like brains is very inefficient. It's not the right way to do things. It's just a big mismatch. And so that's why you end up basically using a lot of power to run these networks. So this is a GPU. Originally developed for gaming, you get one of those, and you can run these your games on it. And it turns out that the reason why it's really great is that it's got a lot of little tiny processors, whereas your computer, your main CPU maybe has 8. This thing has 3,000. Okay, and they actually connect it together so you can pipe all the pixels through them really fast and efficiently. And that's sort of more like the brain. The brain is massively parallel. It's got all these neurons. They are all working in parallel. They're sending information back and forth among each other. So this is sort of the closest we have right now to trying to do this kind of brain-like computing. But one of these GPUs consumes about 250 watts of power. And, it takes like thousands of them, racks and racks of these things to do, to run AlphaGo. Google even made their own specialized GPU chip to do this and so forth. And so, we are very far from getting to the point where, we can build this, sci-fi type robot that's intelligent, that's moving around and interacting with the real world and outsmarting us. Because he's going to need about 20,000 watts of power, and he's going to be weighed down by all his batteries. He's not going to be able to go anywhere. And there'll be, he'll run out of juice in a few minutes, So, we are nowhere near doing this sort of brain-like computing, but with the same kind of efficiency that the brain does. The brain only uses like 20 watts. And so how have we sort of attacked this in the past? Okay, in the past, the way that we've made computers more energy efficient, it's by shrinking their components. It kind of makes sense, right? If I make things smaller, I put them closer together, the amount of energy I need to switch the thing is less, and the amount of energy I need to send the signal around is less. Everything is smaller, more compact. And this is why now, actually, the phones you have in your pocket, back in the 80s, that was a supercomputer, right? Which filled, a whole room, and it was refrigerated, like it was cooled and everything. And so we've seen this process happen. And the other way in which, and this is described as Moore's law, actually. So back in 1965, with this line here, the first integrated circuits or so were developed in about 1960. After about 4 generations, Gordon Moore, who was then one of the founders and used to be CEO and then chairman of Intel, extrapolated that we would be able to basically double the number of transistors we fit on a chip every year and a half. And we've been following that trend for 50 years. Okay? And by shrinking these devices, we're able to use less power, and this is how now you have what in the 80s was a supercomputer in your pocket, in your phone. But something interesting happened over the last decade or so. So if you zoom in from, this last decade, from 2002 to 2017, the last 15 years, this now is plotting how many millions of transistors you can buy with $1, okay? And so you guys are used to it, right? Like, those of you, you got your first cell phone maybe 10 years ago. You were always getting twice as much memory, and things were going faster, was doing more stuff. And it wasn't cost, it was the same amount as, the old model, right? So and the reason what's happening was that as we shrink the devices, they also became cheaper to build, right? And so we went from 2 million transistors for $1 up to like 20 million transistors for $1. But all of a sudden, back in, 3 years ago, the price of a transistor went up for the first time in like 50 years. Okay, and so we reached this point where it's not economically making sense, unless you guys want to pay $2,000 for your next phone instead of $1,000 to continue to make these, to continue to shrink the technology. And why is that, right? I'll talk about that in a little bit. The other strategy that we've used to make computers more efficient is by reducing the voltage at which they operate at. Again, voltage you should just think of as energy. Like, the amount, 1 volt means that an electron, to move it from this part of the circuit to another part of the circuit where it's a 1 volt difference, you need 1 joule if you add 1 coulomb of charge. So it's the energy per unit charge, right? So if you just make the voltage smaller, you win in 2 ways. The amount of energy you use to move that electron is less. And also, the amount of electrons that you move is also less, because when you move those electrons onto this other node in the circuit, the more electrons you put there, the higher the voltage goes. You have to get a certain number of electrons just to get that voltage. So it's a quadratic dependence of energy on voltage. And, so if you look at the graph here now, going from, 6 micron will be back in the 80s to 32 nanometers. This is the size of the transistor, the length. We basically, back about a decade ago, stopped decreasing the voltage. There are many reasons for that, but if you don't do that, you're not going to get things to be lower energy. And so we are basically run into what's called a roadblock. Okay, basically we can make the transistors smaller, but they're more expensive. And we can't reduce the voltage for various reasons, so we are betting more power. So we can't switch the transistors faster, so your clock speeds of your computers are not changing, and so on and so forth. And in fact, even though we can put more transistors on a chip, we can't turn them all on at the same time because they will burn too much power and the chip will melt. Okay, so we are hitting all these different roadblocks, and it's actually, the first time in 50 years that it's happened, right? So this is quite dramatic. It's not like, it's like, we've been using some technique to swim, and we're not gonna. That technique has basically we're at the fundamental limit of how fast you can go if you swim that way, unless you get some flippers or something like that, something completely different. You're not going to change to make the progress. And so, what is that fundamental limitation? And it's everything has to do with physics, right? And, although I'm an engineer, I'm a scientist at heart. I love these STEM, math, physics, and so forth. That's what got me into what I'm doing right now. And it allows you to think from first principles. Like people may be giving you all kinds of reasons why it's doing this or why it's doing that. But it's just physics, okay? So what's going on, right? So if you look at a transistor, right, this is what a transistor looks like, right? There's two terminals, the drain and the source, and the current flows from the source to the drain, okay? And then there's a third terminal, the gate, that the voltage on this gate determines how much current flows. It basically, essentially, they say it creates a channel, okay, for the electrons to flow, okay? And now this is a transistor that's about 30 nanometers wide, okay? So that's about in 2012. That was how, 2012, 2013, this is the kind of devices we're building. But we are getting to the point where you can see there's a limited number of lanes for these electrons to flow. We're getting down to 6 or so lanes, and this is not even your ultimate scale device. Each lane is about 5 nanometers wide, okay? And so what's happening as you shrink the transistor is you're reducing the amount of lanes on the freeway. You can think of it like the 405 freeway, okay? We're down to like where we have like 5 lanes, okay? And, in order to continue to shrink and not lose additional lanes of traffic, Intel in 2014 introduced something called a FinFET, where this bottom part is silicon. They have a fin of silicon sticking out of the device, and the gate wraps around it. That's creating lanes of traffic for electrons to flow on this side, on the top, and on the other side. While at the same time, this transistor fits in the same space as this transistor. So you can you don't reduce the number of transistors that you can fit on the wafer, on the chip, but you increase the number of lanes you have. So now if you shrink it and fit more transistors, you still shrink the footprint, you still have as many lanes as you had before. And this is like, if you're in LA, in the 10 freeway, if you're in the carpool lane, you can go up there on the third level, okay? But, this is going to cost you, right? This is like much more expensive to build in 3D than to build a good old transistor. We've been building transistors like this for 50 years. We never have to change a thing, okay? And now we are getting to the point where we are doing all these very, it's like, LA, you should build like a metro or something, you shouldn't be going that direction. It's just too expensive. And so, they've kept at it, and this is sort of now the cross section. That's the gate, and that's the fin. At 22, 14, these are different processes. Every 2 years, they introduce a new one, and they're getting even more extreme with these FinFETs. Why are they going through all this trouble? Okay, why do you think they need all these lanes in the transistor? I mean, one lane can allow the electrons to flow just fine, right? It should still work as a transistor, right? Well, it's not so straightforward because, like the freeway, accidents happen. Okay, so in a transistor, this is called trapping. An electron that's traveling around along in the channel, there can be a defect at the interface between the gate and the silicon, and it can just jump into what's called a trap. That means that you've remade a bond that was broken, and it's just stuck there. And over time, if it gets kicked around enough, at some random time, it will escape. So what will happen with the current, just like on the freeway, where the traffic goes down to a trickle, you're going to see the current that was flowing in the device go down to drop by, in this case, a drop in a factor of 50%. And then at some random time, the electron gets kicked out by being bumped up against, it's called thermal energy, thermal fluctuations, and the current will come back on. Okay, so this will be a device that has something like 2 lanes. So if you shut down one, you get a 50% drop in current. So as you approach smaller and smaller lanes, these kinds of, switching random telegraph signals, they're called, become so big that it could randomly flip a 0 in the computer to a 1 or a 1 to a 0, and your logic could stop working in your computer. And so this is the reason why they're going through all these lengths, making the transistors much more complicated. They're getting more expensive and so forth. But the question is, do you really have to do this? Okay, so this is, I gave a talk back in October of last year, and, it created quite a stir. And there was a story in the Chronicle of Higher Education that talked about, I was leading the charge against computers' biggest roadblock, which I just described. And, Paul Baskin is the writer, and my favorite part of the article was this part here, where he says the son of Albert A. Du Bois, the professor of history at the University of Ghana, who helped lead his nation's democratic rule, Mr. Boahen did not arrive at the session as a revolutionary, but he may have left as one. So what do they think? What do they think was so revolutionary? Well, so this is you can hear the talk at IEEE TV. There's the inaugural conference on rebooting computing, right? How do we solve these problems? And one of the people in the audience said, during his talk, you could see people's eyes growing to the size of whales and smoke coming out of their ears. But so what I did in that talk, I'll tell you a little bit about what I said. It's fairly technical, but I'll try to explain to you in sort of like non-technical terms. I'll get there in a second, but, let me, now we're going to start talking about the brain, and then I'll tell you about, what I proposed, based on what we know about the brain. This is really cool. I mean, I never imagined that I would see this level of detail of the description of what's happening inside my head, And so, like, each of these, little, orange or sort of, cardinal Stanford colored with the 2 gray on the 2 sides. Anybody know in the audience what molecule that is? What? Yeah, exactly. That's water. Okay. So your brain is filled with water, right? And these are like fat layer, basically. These are lipids. Okay. And they form this sort of 2 layers that forms the insulation between the between the inside of the cell and the outside of the cell. Okay, and what you see here is that these are proteins as a tetramer. There are 4 of them, and these proteins form a pore inside the membrane. There's sort of a big region here, but then it narrows down to a very narrow region here. And these, you can see these little cyan-colored guys are potassium ions that are flowing outside. From inside to outside the cell. The green guys are sodium ions. Okay, and basically, so this is what they call it's called an ion channel. This is a potassium channel. It's selective to potassium. It only passes potassium. And if you actually record, scientists can now record from an individual channel and look at the current flow through the channel. You get the same kind of random switching that you're seeing in transistors as they are getting smaller and smaller. Okay. And in fact, the transistor doesn't really try to, the protein ion channel doesn't try to keep the channel on completely or off completely. It sort of changes the probability. Like basically you see it spending more time off or more time on, but it's always switching. Okay, and this is how you're computing with ion channels, and this is how your brain is doing its thing. Okay, and so biology has found a way to basically squeeze everything down to one single lane and be able to still work, even though you have this sort of random, switching, basically essentially noisy operation. And the way that it does that is that it combines analog computation, okay, this column, with digital communication, this row. Okay, the brain sits in this quadrant. Before World War II, we were building these analog computers, and they used analog to compute basically a set of gears. You set the gear ratios, and you can divide two numbers. You can do all kinds of elaborate. You can add. You can do that just by turning these shafts. They had electric motors driving these shafts, but then they had some very elaborate gearboxes that they used to do computation. And so just because the number of turns of the shaft corresponds to the number, that's an analog representation, right? It's just proportional, right? Digital means you have individual digits, okay? And this one means something 1, this one means 10, this one means 100 or something like that. Analog just means whatever you have is proportional to what you want. And so in the analog computer, using analog both for communicating the information and for computing, okay? And then after World War II, when we developed these digital computers, we switched completely. We are using Boolean logic gates to compute. That's a digital representation. And we are sending ones and zeros around. We're communicating with in digital as well. Now the brain, in order to basically be able to work with these ion channels, uses analog computation and then digital communication. I'll show you what that means in this movie here. So those little flashes and the whooshing sound are these spikes. They are just little pulses of electricity. And those are how neurons communicate with each other. And here you're seeing the ion channels opening and closing to allow ions to flow across the membrane to change the voltage, because those pulses are a pulse of voltage as it travels along. And eventually it gets to the terminal of the axon. This is the output end of the neuron. At the terminal there's a synapse. That's the junction between the axon and the dendrite. That's the input end of the neuron. And you can see those little red molecules were released into this cleft, diffused, and bind to the ion channel, and it opens, and those are ions that are flowing through. Okay, so you've gone from a digital representation, just these discrete pulses, to a analog representation when you get to the other side of the synapse, okay? So because the amount of activity that you get here, or the voltage, the change in voltage, is graded. It could be any level, basically. And different synapses, depending on the strength, depending on how many of these ion channels there are, will give you a big input or a small input. But all these different inputs that are combined just by summing them together, like currents or voltages sum on a wire. And that's analog computation. That's how the neuron combines all its inputs to generate its output. And this is just pointing out that the synapse itself is probabilistic. When the spike invades it, sometimes it doesn't release, and sometimes it does. So this kind of stochasticity is all the way, permeates the system. And then, on the upshot of that is that the brain is able to actually, do an individual operation, which is like activating one of those synapses, transmitting the signal from one neuron to the other through the synapse, using about 20 femtojoules of energy. In comparison to a brain, or to a computer is using something like 20 picojoules. So it's 1,000 times just to multiply two numbers or do even one instruction in a computer. Okay, this is where these differences are coming from and this is why we are burning so much power to do all this brain-like stuff in a computer. Now, this is the 5-point secret master plan that the neuromorphs are you're going to use to take over the world. Okay, so you don't know what a neuromorph is. This is a neuromorph right here. He's looking at this beautiful neuron, and he's basically got his glue and he's got his hammer and everything, and he's working on copying it and getting all its beautiful properties and its efficiency and so forth. And how is he going to do that? Well, this is the technical part that causes stir at the talk. I sort of laid out very clearly how to do this, and I'm just boiling it down for you guys. Basically, compute with analog, which I explained because it exploits physics, and that's essentially free, basically. And communicate digitally using spikes. Distribute a computation across neurons. Basically, that way, if any neuron fails or if any connection doesn't fire, all the other neurons are also there to carry the information. So it's distributed in a way. No one neuron is critical. No one connection is critical. And then you coordinate the spiking among these neurons. That's a little bit more difficult to explain, but this is important so that you don't have them all fire and then all keep quiet, all fire, keep quiet. That will be basically noisy. And so you want to coordinate it, and there are ways of doing that. And you also want to do the connectivity efficiently, because now you've distributed your information across all these neurons. You need to be able to move it around, basically bring it back together from one pool of neurons to other, and so forth. So connectivity is very important, but the brain has very clever ways by using these hierarchical branching patterns to do that efficiently. And so that's the 5-point master plan, okay? And if you're able to do that, you're going to dominate. Neuromorphs are going to dominate digital computing and analog computing, right? It puts you in this sort of unique space. Okay, so this graph explains that. So this is the energy it takes per operation, and this is the precision of the operation, right? So precision, you can think of, like in a computer, if I have 8 bits, it means I can count from 1 to 256. So that's a precision of 1 in 256, okay? So that would be around 10 to the 2, somewhere here. Okay, as I increase the bits, each bit that I add doubles the number I can count. So when I go to 9 bits, I can go up to 512. 10 bits, I can go up to 1024. And so there's this, it doesn't cost you a lot because you're increasing exponentially here. This is actually a logarithmic increase in energy, okay? And so that's very nice, but the part that's not so good is that you start up with a very high cost, even for low precision. That's because transistors are used as switches, and you have to do a lot of switching before you can multiply 2 numbers or do anything interesting. And so, but once you do that, you can increase your precision easily. And then as the technology has progressed, we've gone from 90 nanometer here to 28. These curves have been moving down, right? And like I said earlier, this has plateaued. We are no longer seeing this sort of nice increase, so we can't just wait for these curves to come all the way down here, okay? Now, in comparison, before World War II, in these analog computers, the scaling of analog, the rate at which energy increases with precision is quadratic. So it's a very steep curve on a log-log curve. It's got a slope of 2. I go 10 here, I go up 100 on that axis, okay? And the reason it starts out really low is because analog just uses the physics. So if you want to add 2 numbers, you just put those 2 wires those 2 currents on a single wire. They add together by something called Kirchhoff's current law. Okay, it's a law of physics. It has to happen, and so you basically get this for free without doing a lot of work. But if you want to increase your precision, you have to deal with the noise and the current. The electrons are fluctuating, all that stuff, and that leads to this quadratic increase in energy. Now, by doing this sort of brain quadrant here, where you use a combination of digital and analog, digital for communication, analog for computation, you can actually get on a linear scaling curve where you have the lowest energy per operation over about 5 decades, almost 6 decades, than just a purely digital approach or a purely analog approach. Now, for very low precision, analog will win. For very high precision, like scientific calculations, you want 64-bit precision and so forth, floating point, all that stuff, digital will win. But it turns out that for the kinds of stuff we do, to drive a car, see what's coming in, turn a little bit, this kind of thing, right? We don't need a lot of precision. We need to take tons of data, and we need approximate solutions because we're doing this in real time. We can see whether it's working, we can adjust, okay? And we can learn as we go. So, the regime here is really sort of the sweet spot for brain-like style of computation, okay? And so that's basically the plan. And we are about 80% of the way towards achieving that plan. Like out of those 5 objectives, we've already demonstrated 4 of them, parts of the secret master plan. And I'll tell you a little bit about, let me go back for a second. I'll tell you a little bit about, I can't cover it all, so I'll run out of time. But I'm going to concentrate on how we distribute computation across a pool of neurons, and just to give you a feel for how you can do this. And so, how many people out there write code? Oh, okay, yeah. So, okay, very good. Okay, so this is a good example, right? So you're trying to calculate the length of a vector, right? It's got an x, the components of the vector are x and y. You square them, you take the square root, right? And that's it. But you can also do what they call data flow style of computing. You probably break it down into these steps. But you could also do it this way, where you could basically, like if you were doing this on a programmable logic device or something, you could basically build a bunch of logic to do the squaring. You could build an adder. You could build another squaring thing. You could build a square root guy. And your data would flow through like that to do your computation. Okay. Now, what we do when we do this with a neuromorphic chip is that we actually approximate the squaring operation with a pool of neurons. Okay, so we take the input X and we feed it into each of these neurons, and each of these neurons has a lot of variability. They respond in different ways to that input, partly because of the inherent variability in the devices we're using because it's analog, or also because we can assign each one a different encoding vector. Like we could multiply X by -1 before when we feed it in here, and multiply by +1 when we feed it in here. Okay. So I've color-coded them so that you can see what the tuning curves look like. So this is X changing. The one that we multiplied X by -1, he wants X to decrease and he'll fire a lot. This is the frequency of spiking coming out of that neuron and so forth. And there's guys who are going the other direction and they have different thresholds, okay? And just like in the brain, no two neurons are alike. So this kind of variability you can get for free if you just fabricate your transistors. They come back all looking slightly different, okay? And so you take that, and basically there's something called the least squared problem. So you can actually solve a set of equations to find, basically it's a matrix equation, linear algebra, to find what weight, like basically when I come up with a solution, it will tell me that I should take this curve here, multiply it by -0.2 and add it to this curve, multiply by 1.5 and subtract this curve. And when I add those things all together, I'll get this parabola. Okay, so basically, then this parabola corresponds to x squared, right? This is 0, and x decreases, it goes up, x increases, it goes up. That's your squaring function. So we have a way of solving. Basically, we can do this on a computer. If you give me a set of curves for your neurons, how they respond to input, I can come up with a set of weights that will approximate any function with those curves. Okay? And in fact, you don't have to go break it down at all. You could take the full thing and you could encode the vector in a pool of neurons, and you could solve what are called decoders, set of weights, to give you back your result immediately. Okay? And so this is something, it's called the Neural Engineering Framework. It was proposed over a decade ago by Chris Elliott-Smith and Charlie Anderson, and they came up with a bunch of basically mathematical theory that can allow you to take anything you're trying to compute, or even things like differential equations that you're trying to solve. And you can basically map them onto networks of these spiking neurons, okay? Now, they've got a really nice software called Nango you can download. And so you can start building these networks. So if you look at here, we have a population of 49 neurons, 7 by 7. These are all their tuning curves, that is their spike rates versus their inputs. We are feeding input into these neurons. That's the slider controls how much input they get. And then here you can see inside the neurons, like the dendrites are getting this input and the voltage in the neuron is changing, as you see there. When the voltage hits a certain threshold, the neuron emits a spike. These are all the spikes. When the spikes go through a synapse, they become filtered and they look like these continuous signals with little wiggles in them. And then when you take those signals here coming through the synapses, you scale them by the weights that you solve for, and you add them together, you get back an approximation to the input. Okay, so this is just computing the identity function. Okay? We can do more interesting stuff with the same process, just solving for a different set of weights. We can get any different function of this input. Okay? And we can also do dynamics. What do I mean by dynamics? We can solve a differential equation where the rate at which x changes depends on x itself and some gain, and it also responds to the input. Okay? If you don't have this term here, it's an integrator, right? The derivative of x is that, so it means that x is the integral of that. Okay? And so you can build that. You can say, hey, give it the Nango this math, and it will build you a network. And you can see, in this case, I need a recurrent connection because x feeds back to its derivative. And so I still have an input, and I have a control here that's controlling this alpha term here, which is how responsive I am to X. And so in this case, I can basically, I'm just demonstrating here, this is the input. I give it a little pulse of input. It integrated it because alpha was 0. And then I start increasing alpha and so forth. So this is just showing you it's remembering its past input, which is the feature of a dynamical system or a differential equation. And they basically last 2 years ago or 3 years ago now, they basically used these methods, this neuroengineering framework, to develop something called SPAWN. And this is the first time ever where people have built a whole model of the entire brain. And it's not just a bunch of random activity and waves and oscillations and stuff like that. It actually, they started with a set of equations describing what they wanted it to do, how they wanted it to respond to visual input, how they wanted it to control its arm, how they wanted it to remember what it's seen. And then they could feed it input, and it could respond by writing its answer down with its arm. I'll show you one of the examples of the tasks that it could do. And you'll hear Chris Smith, who did this work, put out this book about the work.
The fifth task is a question-answering task. Spawn is shown a list of numbers and is then asked a question about the list. There are K questions and P questions. Here it is asked a P question, which means it must indicate what is in the position number provided. Here it's asked what is in position 5. This task demonstrates that Spawn has flexible, rapid access to information that it encodes.
Okay. So, this is how you can distribute computation across populations of neurons. And the same principles or the same methodology works for vision, for motor stuff, perception, action, and cognition. Okay, you can ask it sort of IQ level type questions, IQ test level type questions, and so you can look more into that. And so we're collaborating with Chris Smith's group up in Waterloo in Canada, and we've taken that same theory and we've applied it to our neuromorphic chips. So, like I said earlier, when we fabricate the neurons, these are 100 neurons. And we basically fed them all current. It's normalized such that at 0.5, they should start spiking. But because of the variability, different transistors behave slightly differently. Some start spiking when it's 0.2, some don't spike until it's 0.8. You got a huge spread in these in activity. And also, like if I gave all of them the same current, some guys will spike at 20 hertz and some guys will spike at like 90 hertz. Okay? And so normally engineers are scared shitless of this variability. I mean, if you, in engineering school, you're taught that, they give you a spec and 99.9% of them should match the spec and this kind of stuff, right? And the brain, any two neurons are completely different. It's just they're all over the place, okay? And so these are the kinds of things now we're able to do. We're using these methods, we're able to tolerate this kind of variability. We can take these curves and we can apply this neuroengineering framework to come up with a set of weights to combine those spikes by. And essentially, we solve the problem not when we fabricate the chip, but we solve it afterwards when we program. We take care of that stuff, right? And so, we treat these as, if you like, normally you have logic gates. They have some input-output relationship. These are analog gates. They have some input-output function. So we just measure that from the chip. We feed it into the computer. We can solve for all these weights, and we can compute anything that we want. And so I call these physical computational primitives. Basically, they are physically instantiated. We can't change them. It's just said by the physics. But we can use them because now we have all this cool, machine learning and all these techniques. And so we've actually used that. I showed you neurogrid moving earlier. The set of equations that we need to control the robot. For example, the torque that we apply to this joint, the motor in the base here that's rotating this. The torque that we apply to there consists of like 1, 2, 3, 4 terms like this. It's the cosine of this angle Q2, which is this angle, times the sine of Q0, which is this angle on the base, times how much of the component of the force is in the x direction, and so forth. And there's like 3 other terms like this that we have to approximate, and that gives us sum together to give us the torque that we should apply to that joint. Okay, and you can see here, these are the dots. This is what the neural network or the neuromorphic chip gave out after we solved for those weights. and the surface is the mathematical function that we were trying to approximate. Okay, and so then this is how we were able to do a good job controlling the robot. So I'm going to end with this video here, talking about, now if you're able to take these neuromorphic chips and implement these brain-like algorithms, but do it very efficiently with very little power, what's the future? What kinds of things are we going to be able to do with that? Okay, and for that, before I, just to set the stage for that, I'm going to show this video from my collaborators at Stanford. And you see, one of their postdocs, and it's featured prominently in the video. But it's the Shenoy and the Henderson labs.
For decades, researchers have worked to create a better and more direct connection between a human brain and a computer to improve the lives of people who are paralyzed or have severe limb weakness from diseases like ALS. Those advances have been notable, but now the work is yielding groundbreaking results. Special correspondent Kat Wise has the story. It's part of our Breakthroughs reporting and for our weekly segment about the leading edge of science and technology.
Dennis DeGray is a 64-year-old quadriplegic who is writing a sentence on the computer screen in front of him using only his brain. A former volunteer firefighter, DeGray had a bad fall 10 years ago which severed his spinal cord. As part of an early-stage clinical research study led by Stanford University, DeGray and 2 other volunteer participants with ALS had small sensors implanted in their brains in an area called the motor cortex, which controls movement.
Shall we take a look at some stats on how you've been doing?
Sure. Let's see what kind of numbers we got.
67 trials, 1 mistake.
I'm moving in the right direction in the transits.
Even though DeGray can no longer physically move his arms, the neurons in that part of his brain and in the brains of many other paralyzed individuals remain active. The sensors in his brain listen into those neurons, which emit different electrical signals depending on the direction DeGray thinks about moving his hand.
To move the pointer around, I imagine a ball lying on a table with my hand lying on the ball. And as I roll the ball forward, the pointer goes up. And as I roll the ball back toward me, the pointer goes down. And of course, left and right correspondingly.
The neural signals are transmitted to the computer through 2 devices that screw into small pieces of equipment called pedestals protruding from DeGray's scalp. In the computer, sophisticated algorithms turn the movements in his mind into cursor movements on the screen.
It's very liberating to be able to utilize a portion of my body that has not worked to actually cause an effect is great fun.
I'll stop it there. Yeah, fantastic work. This has been about a decade and a half of research going to this area that's now clinical trials. These are not, they're called participants, they're not being treated. They're just doing this because of science, because it's still in the research state. But you'd notice that whole rack of equipment, right? So why does he have these pedestals on his head, and why there's a bunch of circuitry in there and these cables going to that full rack of equipment, right? We can't actually, do this as a clinic, as a therapy right now because of that, right? And what you'd really want is you'd want all that to happen inside his brain, right? You want to implant a little chip that takes those signals and does the control or whatever he's trying to move. And in fact, he's doing this with he's controlling a computer right now, but we want to move to a robot arm or something, like give him an arm or something that he can control. And so the research that I've described, we're on track to basically be able to do that, be able to make these chips consume so little power that we can implant the whole thing inside the brain. It has to be milliwatts of power, thousands of a watt, because you can't heat up the guys, brain. So that's where, you have to match the efficiency of the brain, right? So you can play nice with it. And so that's where we're headed. That's where you're going to see in the future is being able to actually do that kind of stuff and help these wonderful people, really heroic volunteers in these collaborations. Thank you. Okay. I think there's a mic here and a mic over there.
So thank you very much for an absolutely wonderful talk, and congratulations on the fantastic work you're doing. I wanted to ask you, since the focus is on energy and power, I saw a paper a couple of weeks ago in which a neural net was implemented on a photonic integrated circuit by some folks at MIT. They were making the argument that for these, particularly for these very sort of high computational load matrix multiplications, that was a way to save a significant amount of energy. I was curious about since we're rebooting computing,
yes.
I was curious about your thoughts about non-electronic architectures like photonic architectures as part of the solution to that.
Yeah, it's a great question. I'll delve a little bit deeper into this. So we have various kinds of applications, right? So for example, right now, when you're talking to your phone and it recognizes, like say, "Hey Siri," and start talking, right? That speech is uploaded to the cloud, and they have these racks and racks of computers that are running these neural networks to translate the speech. In fact, they don't actually translate your speech. They wait till they get like 200 people speech, because once they load that network into the computer's memory, the overhead and loading it in and loading it out, it takes time. So they want to be able to compute several, it was called batch side, several different speech, translate a lot of speech before then they go on and load the next task, right? So that's sort of a batch style cloud level computing. You want to cycle very fast. And these kinds of applications I've talked about are what are called embedded applications, where we are not doing multiple jobs from multiple people. It's dedicated to a specific task. Either it's implanted inside your brain or it's sitting inside your car and is driving the car, right? In those applications, you're responding in real time, and you are pumping the information through very fast. And so the optical approach, I think, is good for the earlier part, where you can basically batch up to 1,000 speakers, and you can do very fast, because the optical thing runs really fast. It's running way faster than a real neuron. It's making very short pulses, and it's communicating at very high rates. And so it's not so well suited for like a real-time kind of application where you're matching sort of things that are coming in just from one source. So that's the distinction I would make there.
Hi, thank you for the talk tonight. It's been amazing. As an undergrad at Hopkins, I think it's really inspiring. And my question is, if you think that neuromorphic computing is to replace or be integrated into how logic is dealt with and done today, do you think that'll have an effect on how we develop our software or how that landscape looks in the future?
Yeah. I did my undergrad at Hopkins, so yeah. It's very interesting, right? We're still going to call it software, right? I do hardware and I do software. I do the whole stack, but it's a different kind of software. So, we are trying to solve problems that we don't know how to write down the answer for, right? In the case of this robotics application, I can solve all the equations, the mechanics, all that stuff. Right? That's why I got those equations, and then I can sort of map it onto my neuromorphic chip. But in the case of like, a car that's driving, it's getting visual input, it's trying to learn to control the steering wheel. The way that's done is that you record a lot of video, and you also record the position of the steering wheel and the brake, the accelerator, or the gas pedal while the people are driving, millions of miles of this stuff. And you train the network, right? So it's like the real programming is coming out with the rules for how you adjust the properties of the network. But then you let it loose on some data, and it figures out the right mapping, right? So it's sort of like at a higher level, right? Because does that make sense? Yeah, but it's still, if you want to think of programming that way, you move to this higher level where you just deal with massive amounts of data, and you come up with rules for finding patterns in data. I mean, you really need to know a lot of, matrix, linear algebra, matrix, all the stuff, matrix theory, all the stuff, right? But it's very mathematical. Yeah. Oh, over there, Walsh.
Hi. Thank you for this talk. This is great. So you mentioned Google and AlphaGo and self-driving cars and so on. those applications usually rely on convolutional networks and kind of more traditional machine learning. And it's unclear to me how well suited a neuromorphic chip would be to implementing a convolutional net or a deep learning net as opposed to graphic GPU style computer. Could you say something more about that?
Yeah, I can say a ton about that, but the algorithms that you described were developed in the 90s and the 80s, and I've been around. I was around then, I was already in graduate school and finished undergrad. So there's nothing new in terms of the algorithms. It's just the compute power and it's really good, clever fine tuning. Okay, but it's actually so the convolutional neural network was originally developed for taking, handwritten digits and classifying them. Basically, the post office, your postal service paid for that research because they wanted to be able to read the addresses on letters, handwritten letters, right? And this is a very different application from driving a car, okay, or interacting from the real world in time, right? You're dealing with video. And actually, dealing with video, you really want to. Part of the reason why it takes tons and tons of data to train these things is that they're taking every frame of the video and they're looking at it as some random picture from the net. And then you look at the next one, nothing probably changed, and so forth. So they are processing all of these because they have no notion of time or state and so forth. Your brain, when you're driving a car, right, your brain is predicting what's going to happen in the next moment. If what happens in the next moment happens, it doesn't do anything. It doesn't care. If something happens that it didn't predict, then it pays attention, and that's the part it processes very quickly, very rapidly, focuses the resources on. So if the kid jumps in front of the car, you're going to be on it, right? And so this is we are sort of taking this. It's a mismatch, And the techniques this is why I'm talking about dynamical systems, state, and all these kind of stuff. We need to develop a whole new, or there's a much more efficient way to do this when it comes to video than what we're doing right now. And those are being developed, right? And this idea of prediction is key because basically then you can train things in an unsupervised way. Just make the lower levels of the network basically learn to predict the video, and that's how you train them out. And then only the upper levels you have to sort of train to do the specific task. And then that way you get a very sort of robust solution, right? Where these adversarial examples don't work against it. But, I hope I've given you a gist of an answer there. Yeah. So we're just in the beginning, if you want to think about it that way. Yeah, continue.
I just wanted to really thank you for the fantastic speech. As a Hopkins EE, I'm also very excited. I was wondering, currently, what's the biggest challenge that researchers in the field of neuromorphic computing are trying to overcome right now?
Yeah, I mean, it's. I think I would describe it as, kind of this started in the 80s and sort of contemporaneous with the development of the neural network field. There was a lot of work in that first decade, mid 80s to mid 90s on, analog stuff, trying to build large scale analog things because everything was digital. And then the next decade from mid 90s to mid 2000 as well, now we build these things. How do we interconnect them? How do we build we can build more stuff than we can fit on a chip. We want to talk to each other. So then people, went back to doing spiking and communicating digitally, built all that infrastructure. It's a little bit different from your traditional digital bus that you use in a computer. And it's asynchronous, there's no clock, and it's basically dealing with a much larger number of guys who want to communicate than maybe a few processors on a chip. And then I would say from the mid 2000s to now, the focus has been on what I told you in the end, like how do you now make this some kind of programmable device so you can do arbitrary computations with these kinds of chips, right? Then I think now, we've got first examples of this, but now we have to make it more efficient in doing that. This is what I was talking about when I said you have to coordinate the firing of the spikes of the neurons to really get on that linear instead of quadratic curve I showed in my plot. To me, that's the next big step, really making it efficient by adding this sort of coordination mechanism. Yeah, that's the last of the 5 steps in the master plan. That's why we have the master plan. Okay, yeah.
Thank you again. I hope my question is not seen as too off topic,
Yeah.
and I know it's probably not your primary area of expertise here, but given your unique education and your experience, I'm really curious to know what are your thoughts as to where consciousness comes from and how you understand how the brain works. And in 15 words or less, if you want.
No, you mean 140 characters. So I've gotten that question before, and my answer in 13 words or less is, if you have, I'm a nuts and bolts guy. I believe that if you have enough nuts and bolts, you get consciousness. It's just a question of scale, is what I'm saying. And I don't really believe. Yeah, I really believe that. And getting that scale comes down to energy. You need to be able to do a lot of stuff in the same amount of space. But what I'm saying is, what we've learned from biology is like you look at like the brain of a worm, you look at a fly, you look at a cockroach, you look at like a mouse and so forth. You look at humans, you look at apes. We haven't found anything that's unique about us. The same kinds of neurons, same kind of proteins. There's nothing special. We didn't come up with they have cortex, they have, So to me, the biggest difference between us and, the apes and so forth is just the scale. Like we got 100 billion neurons, right? The closest one, the macaque, has something like 7 billion. And, so it's just the scale is incredible. And somehow, that makes a huge difference. This is interesting because we're not used to think about computation in this way because, Turing proved that, the Turing machine, universal computation and so forth. So even the little tiny 8-bit computer I had as an undergrad can do any computation that, your super duper computers you have right now. It's universal in that way. That's not the same thing for neural networks. When you hit a certain size, you go through this phase transition where new things become possible. This is part of why, we didn't start doing a good job recognizing images. We had these algorithms in the 90s. We're building these neural networks, the same backpropagation and everything. But all of a sudden, once we exceeded like a billion parameters, about 1 million neurons, we were doing a fantastic job. We became state of the art at recognizing images, right? But there's nothing different about that size as to the little tiny ones we were building back in the 80s. It's just size is the difference, right? And so there's this, we just don't think, we have to think in a different way about how this neuromorphic computation works. Scale is important. Yeah.
Thanks for the talk. I'm a computer science professor at Georgetown, and I have not really heard much about this style of computing. I definitely don't know anything about biology and neuroscience. But one thing that occurred to me during the talk is that our brains were designed via an evolutionary process that's not perfect and has a lot of haphazard stuff going on, and even among just individuals, I can see from my students, some brains seem to work better than others. So I'm kind of wondering, like, with this approach to computation, how much better than human brains could we hope to do, and what's like the fundamental limits to this approach? Like, in theory, like how much power should it take to do certain computations?
Yeah, I mean, I can't answer. I don't have how far can we go? Okay, but I came at it from the opposite direction, right? So, the reason, I didn't know any biology myself until I got to graduate school, and I hated biology, I mean, so, and the way I got into it is, I was a tinkerer, I used to build stuff and I'll do all these experiments. And when I was a teenager and I got my first computer, I went in the library. I was afraid to take the thing apart. I was intimidated, but, so I went in the library and I read everything I could about computers, and, I thought it was brain dead. I thought it was so dumb. Like you start with zeros and ones. You could have any level in between. You only use 0 and 1, and then you do an AND and an OR, and then you have to pack so many of these things together to do a multiplier, and then you have to run the clock so fast because you have to do all these instructions before you get anywhere and stuff. So actually, what I'm saying, I was turned off from computing. I thought there had to be a better way. I didn't know any biology. I didn't know how anything of the brain did. But then these neural networks back in the late 80s, I was a freshman in 1985. Backprop and HuffFuelNet, all this stuff came out around 86, 87. And I built my first neuromorphic chip trying to implement some of those ideas as an undergrad. And it didn't work. It was terrible. And so then I was like, no, these guys, these equations don't really describe what the brain is doing. And so I was like, but I thought it was very elegant. Like you could train a backprop and so forth. You didn't have to write all this code and so forth. And you could do, so I was sold. But I wanted, the reason I was sold because I could see what computers could do here, and I could see what these things could do, and I could see the amount of stuff computers needed to do their stuff, and the amount of stuff these guys were doing with so few neurons and so forth. So, and then I started to understand energy and how much computer uses in the brain. At that point, it was like 1,000,000 times worse. Computers 1,000,000 times worse. So I was just sold. I didn't care. 1,000,000, that's huge. I don't care what I can go beyond that. I just want to get there. So that's where I'm coming from. I haven't tried to, I've become actually much more humble when I think, it's humbled me in some sense, learning about biology. That's what I'm trying to say. Yeah.
Thanks.
Yeah.
So I have a question from our Carnegie Facebook page. Someone is wondering if you have a timeline for how long, if ever, we'll see some of the concepts that you're working on in your lab in daily applications that we use in our regular lives.
Yeah, it's an excellent question. Apart from the sort of brain-machine interface stuff that we're actively working on as one of sort of our pilot, applications. Think about, you guys out there should think about, so we used to have laptops, right? And now we basically do everything on this thing, right? You don't even open up your laptop, right? You're basically trying to do all the stuff because it's like so convenient, it does all this stuff, right? And, but these are going to go away, right? You're going to have the same jump you had from the laptop to this, to the next device, right? It's going to be like this small. It's going to run for the whole day. The battery is going to be this tiny thing. It's going to be sitting behind your ear here. And you're going to basically, now we can see, computers can see, they can hear. It's going to interact with you in a natural way. We're going to beam the stuff back into your eye and so forth, right? That's what it's going to be. You're going to be wearing this stuff. It's just going to be there all the time. It's going to be putting stuff on the real world, augmented reality. How are you going to do all this stuff in this little device, right? You need the same jump, like this thing here. Your laptop uses about 20 watts. Your phone uses like 1 watt. You need the same jump down to maybe a tenth of a watt doing all this stuff, okay? And so that's where you're going to see, this stuff come into play, where the form factor, the next form factor, the next device, and so forth, okay?
Hi. Thank you a lot for your talk. It was very interesting.
Thank you.
I was told to announce that I was beat the last question.
The last Hopkins guy, or
yeah.
Okay.
So one of the major problems and bottlenecks of neural nets is that it takes a long time to train. Given that these neuromorphic systems are like very unique when you produce them, given the variability of the transistors, and you need to set the individual weights and whatnot. Can you speak a little bit to the scalability of the production?
Yeah. So this is actually also, somebody asked about what's the biggest roadblock. It's very interesting, right? So it takes a long time to train these devices. These deep neural networks on these GPUs. And I've already alluded to that. Part of it is basically trying to treat each frame as a random image. But instead of developing techniques to deal with video, could actually make that much more efficient. But then eventually we want the chips themselves, the neuromorphic chips themselves, instead of training offline and downloading onto the chip, we want to do the training on the chips themselves, right? Now this is a big challenge because if you look at the precision that's required, they're running these GPUs. These GPUs have floating point, precision. And it turns out with training, you need a lot of precision. After you train the network, you can actually truncate the weights down to low precision, and it still works. And but there's no learning algorithms right now that do learning with low precision components. I think this is what you're alluding to in your question. But on the other hand, the brain does that. Like you look at a synapse. Yeah, I showed you. It's like this very probabilistic thing. It's noisy. It doesn't have very many bits of precision and so forth. And so that's still missing, that sort of gap there as to how you can do this learning with low precision components. Is still there's some ideas, people are working on it, but that's research, future research. Yeah.